Alright gang, it's at 11:50. Going to be a lot going on in this video. What I want to do first is I want to work a couple of examples. So work examples on my math lab. That's always a good primer for getting you ready for your assignment. And then I want to talk about errors and power. You may have been kind of curious, what's up with this alpha 0.05, alpha 0.10? Is that just an arbitrary choice? Well, it actually turns out that it's tied into what we call type 1 and type 2 errors, and power definition will evolve from that. So guys, let's go to my math lab and I'll show you what I'm going to use here. Now, depending on the semester that you take this, I'm pretty sure this was set up for my summer 2017 class. So if you're taking this in a future semester, it may look a little different. But nevertheless, there is an assignment right here that says hypothesis testing for proportions, practice problems, not for credit. So you don't get any credit for doing this one, okay? So I'm just going to use this as an illustration and a teaching tool. All right, so the first problem said, according to one source, 52% of plane crashes are due at least in part to pilot error. In a random sample of 100 separate incidents, 65 were due at least in part to pilot error, complete A and B. So we want to test that the proportion of airplane is not 0.52, so we're going to have P equal to 0.52. Remember, the null hypothesis is always equal to. And we want to test not equal to, so not equal to 0.52. So if we didn't make a typo, do something goofy, we know we're going to get that one right. Determine the test statistic. Well, I think the easiest way to do this is to use StatCrunch. So I have, 65 out of 100, testing 0.52. So I'm going to go to stat, proportion stat, one sample with summary. So guys, I've already forgot. It's crazy. 65 out of 100. I'd much rather be safe as have to put up another video. And we are looking at 0.52. And we want not equal to 0.52. Everything look good? And compute. The test statistic is under the Z statistic, so it's 2.0 or 2.602. So we'll see how many places we're supposed to go to. So it's only 2 places, so 2.60. Determine the p-value. What's the beauty of having this? P-value is 0.0093, rounding to 3 places, so that'll be 0.009. What is the proper conclusion? Well, guys, we know we're going to reject because our p-value is less than alpha. Our alpha was 0.05, so we're going to reject H sub O. So there is sufficient evidence to conclude that the population proportion is not 0.52. Determine the correct interpretation of the rejection decision. Well, we rejected, so we're believing that the alternative hypothesis is more believable. So the percentage of plane crashes due to pilot error is significantly different from 0.52 because the p-value is less than the significance level. All right, question number 2. Suppose a pool is taken that shows 780 out of 1,500 randomly selected independent people believe the rich should pay more taxes than they do. Wow, getting a little political here. Cool. Test the hypothesis that a majority, more than 50%, believe the rich should pay more taxes than they do. So guys, remember, P always has to be equal to, so it can only be B, C, or D. And then we're testing more than 50%. So guys, it looks like to me C has the equal sign in the null hypothesis. And since we're doing majority greater than 50%, we would do the greater than in the alternative. Find the test statistic. Again, I'm going to write this down because I don't feel like coming back over. So we're looking at 780 out of 1500, and we're testing 0.50, and we're testing greater than. All right. Easy stuff. Proportion, one sample with summary. Number of successes was 780. Number of observations was 1500. P is 0.5, and we want to test majority, so greater than 0.5. All right, so the z-stat is 1.55, rounded to 2 places. And the p-value is 0.061, rounded to 3 places. Guys, you can always pause the video. That's a beautiful thing about taking this class online and having the lectures videoed. If I was in class and I was going this fast, it'd be hard to keep everything straight. Guys, stop me, pause me, take screenshots, all sorts of creative ways to get it done. Do you reject or not reject? Well, guys, our p-value is greater than our alpha, so we're not going to reject. So the correct interpretation, if we don't reject, then we are buying into the null hypothesis. So P is 50%. So the percentage of people who believe is not significantly more than 50%. All right, guys, that's it. Let's go back over here and start talking about errors. All right, guys, the way to present errors is to look at a 2x2 table, and the H sub O that we present can be thought of as either being true or false. So let's go back to the H sub O, that the percentage of people who feels that this is just the problem we just worked. Percentage of people who feels that the rich should pay more taxes is either 50% or it's not. So that statement we can think of as either being true or false. The decision that we end up making is either to reject H sub O or fail to reject H sub O. Now let's look at these 4 outcomes and determine the impact. If H sub O is true, which one of these decisions do we hope we make? Do we want to reject a true statement, or do we want to keep a true statement around? Well, we want to fail to reject if the statement is true. So I'm going to put a smiley face there because that's a result of the test that we hope happens if we have a true null hypothesis. If the null hypothesis is false, which one of these decisions do we hope we make? Well, we hope we reject false statements, right? So I'm going to put a smiley face because that would be the end outcome there. Now, guys, in playing along with me, you've got to understand we never know whether this is true or false. It's a statement about the population. We go out and take a sample. We do our best estimate of assessing the truth of that statement. So we never know true or false. But it's got to be one of these two. We make a decision, reject or fail to reject. If we fail to reject a true statement, then the test ended up the way we hoped it would. if we reject a false statement, then the test ended up the way we hoped it would. But what happens right here and right here? Well, guys, I'm going to put a 1 and a 2 here, and I'm going to put an alpha and a beta there. Why? Because we run into errors. This would be an error. This is rejecting a true null turns into an error. That results in an error because that's not the outcome we want. And it turns out that is precisely what we call a type 1 error. Down here is what we call a type 2 error. I put alpha in this box because alpha, the level of significance that we set in every test of hypothesis, is the probability of committing a type 1 error. Beta is the probability of committing a type 2 error. Now, your head's probably swimming, probably thinking, Darbo, you're talking too fast. That went over my head. Well, guys, we need to write this down. Okay? So let's put this stuff here. I'll tell you what, let me... So, first of all, let's talk about a type 1 error. A type 1 error is what? Rejecting a true null hypothesis. A type 2 error is what? Failing to reject a false null hypothesis. Alpha. What is alpha? Alpha is the probability of committing a type 1 error. Hopefully you can see that, but you can't, can you? All right. What's beta? Beta is the probability of committing a type 2 error. So a type 1 error is rejecting a true null. Type 2 error is failing to reject a false null. And alpha is the probability of committing a type 1 error. Beta is the probability of committing a type 2 error. Guys, very important here. Power is 1 minus beta. Power is the probability of rejecting a false H sub O. That's the purpose of any test of hypothesis. If the null hypothesis is false, we want to have enough power to be able to reject it. Now, guys, there's a lot more going on here. But again, this is an introductory class, so we want to keep it kind of in an introductory level. Now, let's think about this a little bit further. Errors are bad, right? We don't want to commit errors. We typically set alpha at 0.05, which tells us there is a 0.05 probability of committing a type 1 error. But in a previous video, I told you that alpha equal 0.01 was a reasonable choice for alpha as well, right? Well, if I come up here and set alpha at 0.01, then there's only going to be a 0.01 probability of committing a type 1 error. And if errors are bad, if you commit one only 1 out of 100 times versus 5 out of 100 times, you're committing them at 1/5 the rate. Why wouldn't you set it at the lower value? Well, guys, it turns out that as alpha increases, beta decreases. As beta increases, alpha decreases. So we get this opposite reaction when we set alpha higher, then the probability of committing a type 2 error decreases. When we set beta higher, the probability of committing a type 1 error decreases. So a way of kind of thinking about that is to examine the 4 levels of alpha that I told you in a previous video that we may use. Guys, if you set alpha really, really low, then you are rarely, only 1 out of 1,000 times, are you going to commit a type 1 error. As you let alpha increase from 0.01 to 0.05 to 0.10, you are often going to commit a type 1 error. However, because these two things work inversely, if you close the door for committing a type 1, you open the door for committing a type 2. If you often commit a type 1, then you're rarely going to commit a type 2. So what people do a lot of times, instead of investigating the effect of a type 1 and a type 2 error to see which one is worse, because if a type 1 was a worse error, then I would rarely want to commit one of those, so I would be inclined to set my alpha lower. However, if a type 2 was worse, I would be inclined to set alpha higher because I would want to rarely commit a type 2 error because it is worse. What people do typically in research is they don't want to think about all that stuff, and they just kind of choose the middle ground and go with 0.05. That's usually what happens. Now, what happens with power? Remember, power is 1 minus beta, and beta is the probability of a type 2 error. So we'll always put beta in the column for a type 2. We'll always put alpha in the column for a type 1. So power being 1 minus beta, as beta gets bigger, our power decreases. Right? So if we have a bigger number here, smaller number, if we take a smaller number away from a 1, let's just say our power is 0.1 versus 0.5, I mean our probability. If I take 0.5 away from that, I get a smaller number. If I take 0.1 away from it, I get a bigger number. So a low alpha results in what? A low power. A higher alpha results in a higher power. Higher power, that sounds almost religious, doesn't it? We're talking about statistical power here. So, guys, we start with this inversely. So power kind of works inversely of the probability of a type 2, and type 2 works inversely of the probability of a type 1. Now, what I really want you to know, I want you to know everything, but I got to keep it real here. If we have a reported power of 82%, what does this tell us? There is a 0.82 0.82 probability of rejecting a false null hypothesis. Guys, at the end of the day, that's what I really want you to know. Second thing I really want you to know, well, not really the second thing, about the 730th thing in this video I want you to know is how to interpret a type 1 and a type 2 error. So let's go back to our original problem that we worked with the percentage of people who think that the rich should pay more. We tested 0.05 versus P greater than 0.05. Think along with me here. What would be a type 1 error? Now, let's go back to the textbook definition. If I can find it. A type 1 error is rejecting a true null. So in the context of this problem, a true null would be that the percent, actually it wasn't 5%. You guys are probably sitting there screaming at me. It was 50%. A true null would be that the percentage of people who think that the rich should pay more taxes is actually 50%, but we reject that falsely, commit an error, and conclude it's higher than 50%. So put that in words. The type 1 is what? P equals 0.50 but we reject H sub O. What's type 2? Let's go to the textbook definition. Textbook definition of a type 2 error is failing to reject a false null. The null is false. We fail to reject it. P is not 0.50. But we fail to reject that statement. Guys, it's all I've got. Semester is about to come to an end. Some of you will be glad. It's always good to get a class behind you, especially when you get it behind you successfully. So that's all I got. Take care.